Bismillahirrahmanirrahim. In today's video, we'll be solving example 6.11 from Mr. Sedra's book, 6th edition. And this question also includes example 6.10, which we'll see now. Okay, so this is example 6.1, the circuit diagram given. We want to analyze the circuit to determine voltages at all nodes and the currents through all branches. So all node voltages and current through all branches we have to find. Okay, now let's see example 6.10. Same type of question, determine the voltage of all nodes and currents through all branches. Now in 6.10, this is the circuit that is given, and 6.11, they have added this circuit. So first we'll have to solve 6.10 basically. And the total circuit will be like this, and what we need to find here is the voltages, like voltage here, this voltage, VE2, VC1, and the currents through all branches. Okay, so we start with the 6.10. First step in the analysis consists of simplifying the leftmost circuit using Thevenin's theorem. So we'll simplify this circuit by using Thevenin's theorem first. And I hope you know that we can find this voltage simply by voltage division rule. The total voltage 15 volt divided by total resistance multiplied by this resistance, which is linked to the ground. So 15 divided by 150 and then multiplied by 50 will give us 5 volts. So VBB will be 5 volt. And then we have to find the equivalent resistance or Thevenin resistance, and for which, if you recall, we have to remove the source. The source we put 0. This is also connected to ground. This is also connected to ground. So the circuit will be something like this. That means these two resistances are in parallel. And solving these two resistances in parallel, we get the R Thevenin, or our equivalent is 33.3 kilo ohms. So our circuit will now become like this. This is the Thevenin part, and with that we connect the right-hand side of the circuit. And now we can write the KVL equation here to find current IE. Okay, so loop 1, we start from here, minus VBB, then plus IBRB, okay, so we have this equation, minus VBB, IBRB, then they drop here, which is VBE, and they drop in RE resistance, IERE. Now we'll arrange this and bring the voltages on one side, and from here, now we want to eliminate IB. For that, first of all, we have to assume that the transistor is in active mode. And when the transistor is in active mode, then we can apply this rule that beta plus 1 IB is equal to IE, or IB is equal to IE over beta plus 1. So assuming it to be in active mode, now we can replace IB by this value here. So replacing and then simplifying, we get IE to be these values. And then now we'll put in the values. Beta is equal to 100 is given in the example 8.10. Okay, so VBB, we got 5 here, VBE 0.7, and RE we had calculated, RE is given here 3, RBB we had calculated 33.3, and beta is 100 plus 1, so 101. So the answer will be 1.29 milliampere. So this is our IE, 1.29 milliampere. Now from here, using this formula, we can calculate IB. So using the formula, putting in the values, IB is 0.013. Actual value is this, but we are assuming, approximating it to be 0.013. So this is 0.013. Now let's move to the next slide. Okay. Now we can find VB, the voltage here or here, which is equal to VBE, and the voltage drop in this. So VBE is 0.7 and IER is 1.29 into 3. So VB will be 4.57 volt. Now note, this is different than what we had calculated only for this, which was 5 volt. Because of the circuit loading, the value will vary, or it has changed slightly. Okay, so VB is 4.57 volt. Now VE, this voltage here, is simply IERE, that is 3.87 volt. And then we come to IC, collector current, this one. Collector current, we know IC is alpha times IE. Alpha can be calculated from this formula, beta divided by beta plus 1, which gives alpha to be 0.99. So putting in that value and value of IE, IC is 1.28 milliampere. So IC is 2.8 milliampere. The same current actually will flow through this because there is no division here. It's not going out. So this is IC and this is also IC. Okay, so IC known. Now we can find VC. VC is this voltage here. So the 15 volt minus drop here will give us VC. So 15 minus ICRC is 8.6 volt. Okay, now we need to find these two currents. IBRB is easy. This is the voltage divided by the resistance. We get it to be 0.09 milliampere. And now this current will be the summation of these two. So IRB1 will be 0.013 plus 0.09, summation of the two, so 0.103. Okay, so this far we have calculated everything that we need. And now we can join the second part. So this is the second part that we can join with the circuit. Let's consider the complete circuit now. Assume that Q1 is still in active mode, and therefore the calculations that we had made earlier, they are all valid in this circuit as well. So we can say that these values are valid. All we have to do is calculate the remaining values from here. Okay, however, the collector voltage will be different than the previously calculated. So important point, earlier this current was not divided. IC was going through this, all of it, but now it is dividing it into two parts. And therefore, the VC1 will change, the collector voltage will change. Now, as a first approximation, we may assume that IB2 is much smaller than IC1. So this current we are neglecting. So if you neglect this current, that means the current is not dividing. And so the previous scenario or the previous situation will be valid. So let's see. We may assume that the current through RC1 is almost equal to IC1. So since it is not dividing, because we have assumed this to be 0, therefore this current and the current this is the same. Therefore VC1 is approximately equal to 15 minus ICR1 that we have calculated earlier, the same, 8.6. So even when we connected this circuit, this voltage did not change because we have assumed this current to be 0. Okay. Thus Q1 is in active mode as has been assumed. Now, how do we say that it is in active mode? If you recall the NPN transistor, this has to be forward bias and this is reverse bias. So you can see the voltage here is 8.6 and this is 4.5, and therefore this is reverse bias, and this is forward bias because it is 4.5 here and the other end is grounded. So Q1 is in active mode as we have assumed earlier. Okay, so that's done. Now as far as Q2 is concerned, now this Q2 is PNP transistor. Keep in mind, we note that its emitter is connected to 15 volt through RE2. So this is the emitter connected to plus 15 volt through this. It is therefore safe to assume that the emitter-base junction of Q2 will be forward biased. Now, if you recall the NPN transistor diagram, if this is positive, positive is emitter and the negative is the base, or we can say that positive is more positive and base is less positive as it is here. Positive is 15 volt through this and the base is 8.6. Therefore, this is forward biased. So base emitter junction of Q2 will be forward biased. Now, the emitter of Q2 will be at a voltage VE2. Now, this the emitter will be at voltage VE2, which we can calculate to be VC1 from here, VC1. And this voltage, this is now in case of a PNP, this is base emitter, which is 0.7. So 8.6 plus 0.7 will be 9.3. So VE2 is 9.3 volt. Then we coming to the emitter current of Q2. Now this one is simple. The current 15 minus this voltage 9.3. So 15 minus 9.3 divided by 2K. So 2.85 milliampere is the emitter current. Okay. Since the collector of Q2 is returned to ground via RC, now this is collector returned to ground via RC2, it is possible that Q2 is operating in active mode. Okay, now we had seen that this one is forward bias. This has to be in the reverse bias. Now this voltage you can see is 8.6 and this is ground. Therefore, this will be, if you see this diagram, the base is positive and the collector is negative or lower than the base. Same case is here. Therefore, this transistor is in active mode. So it should be in active mode. So we assume this to be the case. Now, since it is in active mode, the equations is valid again. Alpha and beta equations. So we can write IC2 to be alpha IE2. Now alpha remains the same, 0.99. IE2 we have already calculated this to be 2.85. So multiplying this, IC2 will be 2.82. So this is 2.82 milliampere. Now, what is left is VC2. So VC2 is simply ICRC, so 2.8 and 2.7K, so 7.62 volt. Okay, so far, this is the answer, completed answer, with the assumption that this current is 0. Now, because of this assumption, there will be error. Okay, now since VC2 is 7.6, which is lower than VBE, so because this is 8.6, this is lower, therefore this transistor is definitely in active mode as we have assumed. So it is first of all confirmed that this is in active mode. And now coming on to what I was saying, we have calculated this far this. Now, it is important at this stage to find the magnitude of error because of this assumption. occurred in our calculation by assumption that IB2 is negligible. So as a first approximation, we may assume that IB2 is much smaller than IC1. So this we had already assumed that this is much smaller or negligible. But what is the actual value of IB2? That we can now calculate. The actual value of IB2 using this formula. IB2 is IE over beta plus 1. So IE we have calculated 2.85 divided by beta plus 100. So IB2 is 0.028 milliampere, and it is not 0. So it is 0.028 milliampere. Now, what will be the effect of this? That we have to see now. If desired, we can obtain more accurate results by iterating one more time. So we repeat the whole process one more time if you want to get more accurate values, this time with IB to be 0.028 milliampere. Let's see that. The new values will be current in RC1. Now this current in RC1, here RC1 is IC1. Now this is RC1. Now initially we had said that this is 1.2 and this current is also 1.2, but now since the current is adding, IB2 and this IRC2 is equal to IC1. So from here we can see that the current in RC1 is IC1 minus IB2. If you take it on this side, then what I'm saying is correct, that the current in RC1 plus this current which is coming into it will be equal to IC1, this current IC1. Okay, so from here, the RC1 current is 1.252 and it is not 1.028. So we replace this. First change, then VC1, this voltage VC1 now, because of this change, it will be 15 minus 5 multiplied by this current, it is 8.74 and not 8.6. So change that. And then we come to VE2. Now VE2 is this one here. It will be how much? 8.74 here and 0.7 here will give us VE2, which was 9.3 earlier. It will now be 9.44. Okay, next we come to the current IE2. Now this current IE2 will be 15 minus 9.44 divided by RB or 2. So it will be 2.78 milliampere. This current here will change to 2.78 milliampere. Then we come to IC2. Now IC2 is alpha times IE 0.99 and IE 2.78. So it is 2.75 milliampere instead of 2.82. So 2.75 milliampere. And VC2 is this. Again, the formula remains same. This current multiplied by 2.7, it will be 7.43. So 7.43. And then IB2 again. Now we had assumed it to be 0.028 in the previous case, calculated, not assumed, calculated. But now this will also change, and this will be 2.78 divided by 101. Now 2.78 is the emitter current. So IB is emitter current divided by beta plus 1. So it will be 0.0275 milliampere. This current here will change. So this is the completed and updated values that we are getting. Let's see any other. So this is what we have got, and this is what the book is giving answers. So they're the same. And so final answer, you can write it to be like this. So I hope you have been able to follow this. Please let me know through your comments. Thank you.